Hello, and welcome to today's topic, which is Riemann sums. It's a fairly involved topic today, so feel free to pause the video or come back to it if you need to go over some details. But we'll start right here. Okay, so as we looked last time, we're looking for areas under the curve, and we define that as this definite integral. And there are certain shapes we could do that with fairly easily, rectangles, maybe circles, semicircles. But what if we want to find the area under the curve f of x equals 4x minus x squared from x equals 0 to 4? Okay, we want to find that area. So as always, a picture helps. Okay, here's the curve. It goes from 0 to 4, nicely shaded there. Okay, so what is that area? Well, there's no easy way of knowing. I guess we could say it's definitely less than 16. Right, if we do a 4 by 4 square, it'd be less than that. I guess it's more than 0, but other than that, it's a little hard to say. Okay, so we're going to start by estimating that area, okay? And the whole idea of these Riemann sums is that we can estimate and get our estimate really, really good until it's perfect. Okay, so we're going to estimate the area under that curve using rectangles. And we're going to start by using the left-hand rule. And what this says is we're going to take these rectangles, in this case just 4 rectangles, and we're going to take the height of each rectangle to be the value of the function at the left-hand end of that rectangle. Okay, so if we see that here, so the very first rectangle, in fact, has no height at all. Okay, at the left-hand end of this rectangle, x is 0, so f of x is 0, so the height is 0. If we look at the second rectangle, okay, we get this point here, right? The x is 1, so this is f of 1. Well, f of 1 is 3, so the height of the function here is 3, and therefore the height of this rectangle is 3. And then similarly, the next rectangle is 4, and the next rectangle is 3. We'll also notice the width of each rectangle. In this case, it's very easy. The width of each rectangle is just 1. And so we know that the width of the rectangle is 1. The area of the rectangle is simply the height. Okay, so these rectangles have height 0, 3, 4, and 3. Putting that into this notation, we get f of 0 times by 1. Okay, that's the height times by the width in each case. F of 1 times by 1, f of 2 times by 1, f of 3 times by 1. And so sure enough, we get to 10 to be the area under all those rectangles. Remember, that's the estimate for the area under the curve. Okay. Well, we can do very similarly, but instead of using the left-hand rule, we can use a right-hand rule. So we just flick between these. The left-hand rule, the rectangles are there. The right-hand rule is here. And this, as you might imagine, we take the value of the function at the right-hand end of each rectangle. So now this first rectangle finishes at 1. Therefore, its height is f of 1, so this is 3. And then we get 4, 3, and then 0 again. And so the area of the 4 rectangles, well, this time it's f of 1 times by 1. Notice we just start at 1 now instead of 0, and we end at 4 instead of 3. And it turns out we get 10 again. Now, that's actually to do with the symmetry of this shape. That won't always be the case, that you'll get the same estimate with the right-hand rule and the left-hand rule. Okay. There's one more possibility, which is the midpoint rule. So each of these rectangles, we're going to take the point sort of halfway along, and we take the height there. So in this case, between 0 and 1, of course, is 0.5 halfway. So f of 0.5 is 1.75. And similarly, we get 1.5, 2.5, and 3.5 here. And so now our values are 1. And again, the width of the rectangles is just 1. In each case, that's nice and straightforward. So we get 1 times by f of 0.5, f of 1.5, and so on. And that, in fact, equals 11. Okay, before we carry on, as we're adding these things up, we're going to have a little look at summation notation. This may be familiar to some of you, but if not, here it is. So here is something that's just say we want to sum a1, a2, a3, a4, all the way up to a9. And already that's kind of cumbersome to write them all out. And of course, if we went to 100 terms, there's no way we'd ever want to write the whole thing out. So instead we use something that looks like this. Okay, so the I here is the index of summation. Okay, the thing that's all we count up. We have a lower bound and an upper bound. So in this case it's going from 1 to 9. And then the thing we're adding is we'll call the summand. That's what we're going to add. Okay, so that's our summation notation. Just a few rules and properties of summations. First one says that if we're summing a constant, so we're just adding, for example, let's say we're just trying to add 3. 3 plus 3 plus 3 plus 3, 10 times. Well, hopefully it's clear that that would just be 30. We just have the 10 times by the 3, and that's what this gives us, c times by m. The next rule says that if we have the sum or the difference of two sums, we can add them and subtract them. And then number 3 says if we have a constant multiplied, we can take that outside. The fourth one really just breaks the sum apart. We can still find it. And then numbers 5, 6, and 7 are just some little rules we'll see, and you can prove each of these. There's some nice little induction proofs you can do for these. So the first one says if we just simply sum I, so there's 1 plus 2 plus 3 plus 4 and so on, well that equals n plus 1 over 2. Number 6 says we sum I squared, so 1 plus 4 plus 9 plus 16 and so on. That would be n plus 1, 2n plus 1 over 6. And finally, if we sum I cubes, we get n plus 1 over 2 all squared, and we'll use those in a second. Okay, so we want to just practice using the summation property. Suppose we want to sum from I equals 1 to 8 of 3i minus 2. Well, just what this is, well, this is 1 plus 4 plus 7, and so on up to 22. Just plugging in I equals 1, I equals 2, and so on and so on. Okay, but we want to use our summation properties. So the first one says, in fact, we guess we're using 2 here. If we have something subtracted, we can break it apart. So these are the 2 rules we're using here. And we can also take that constant outside. And now we can apply these 2 rules. Okay, that if we have the sum of the I, it's n plus 1 over 2. And if we have the sum of the constant, it's just that constant times by the upper bound of the sum. And so, having worked all that out, we can get that's 108 minus 16, which is 92. And of course you can check that, because this is relatively small, we can check that just by taking the sum. But in general, as these get bigger, this won't be the case. Okay, so we'll go back to this integral that we saw at the start now. So we're going to integrate from 0 to 4, 4x minus x squared dx. Okay, and to do this, we're going to break the interval into 16 sub-intervals. Okay, we saw it previously, we broke it into 4, now we'll break it into 16. So to go from 0 to 4, we're going to label 0 as x1, we're going to go all the way up to 4, which is going to be x17, and then each of the xi's we can simply find as x1 plus I minus 1 times by delta x. Now delta x is the gap. Okay, so this little gap here, delta x, well, we go from 0 to 4 and we break it into 16. Okay, it's going to be 4 minus 0 over 16, so each of these is going to be 0.25. Okay, and as we go up from x1 to x2 and so on, we're simply adding on one more delta x. So for example, if we wanted to find what x10 was, so x10 would be x1 plus 9 times by delta x, which is 0.25. So it's 0 plus 9 times by 0.25, or 2.25, and sure enough, that's where x10 is. Okay, so that gives us the value of each of the xi's. Okay, and we'll use the right-hand rule this time. We can use the left or the right-hand rule. We'll use the right-hand rule. So the ith rectangle has height f of xi plus 1. Okay, it's not the first one. We always start sort of one further on, so that's why it has height xi plus 1. No, f of xi plus 1. Okay, and I think a drawing would certainly help here. Okay, so here are our 16 rectangles. Okay, so the first one has height f of 0.25, then f of 0.5, f of 0.75, and f of 1, and so on. Okay, and so we can say that the integral there is going to be approximately given by, and it's the sum of all these rectangles. Okay, we have these 16 rectangles we can add up, and the height of each rectangle is given by this term, the f of xi plus 1, and the width for each rectangle is given by this delta x, remember that was 0.25. Okay. In fact, there is your delta x. So your delta x is 4 over 16, which is 0.25, and the xi plus 1 is I times by xi. And just remember why that is. We're bringing the rule here. Well, x1 is 0, so we're just adding an I delta x each time to get the next xi plus 1. Okay, so let's work through this, and this will take a bit of doing. Okay, so we've said that the integral here is approximately equal to the sum from I equals 1 to 16 of f of xi plus 1 times by delta x. Okay, but if you recall from the previous slide, we saw that xi plus 1 is just I delta x, so we can substitute in there. Well, then we can apply what the function is. This is f of I delta x, and so applying what the function is, which is 4x minus x squared, we get this. We can distribute this delta x now, So now we get a delta x squared, and we get, well, in here we had a delta x squared, so we get a delta x cubed here. And now you can use our properties of our summations, just as we did previously. We can factor all the constants outside. Remember, delta x is a constant, 4 is a constant. We can break it into two sums. And we're almost there. Now we have these two terms. Again, we have those summation rules for those. Just a reminder what they are. And so we're to here. So the sum from I equals 116 of the i's is 16 times 17 over 2. And we get something else from the formula here for the I squareds. And really the only step we have left here is to calculate this. When we plug in delta x was 0.25. So we can plug that in. And sure enough we get 10.625. And that's giving us an estimate for the area under that curve. Okay, so just a quick definition of our Riemann sums, just to sort of formalize what we've been seeing. So f is defined on a closed interval, and delta x is a partition of that. We set a to be x1 the first term, we set b to be xn plus 1 the very last term. We call delta xi the length of the ith subinterval, so the little width there. And so we take this sum, and this is what we've been using, from I equals 1 to n of fci delta xi. That's called the Riemann sum of f on a to b. Okay. Some sort of ideas about the Riemann sums. We'll almost always see it being the case where the subintervals actually have equal length. Okay, we very rarely have them at different lengths. Therefore, the delta xi is simply delta x because they're all the same, and that's just b minus a over n. So we take the whole width of the interval and divide it by m. The ith partition is simply given by xi equals a plus I minus 1 delta x. And this makes the xn plus 1b, the last term. And then we have these three possibilities. The left-hand rule summation is f of xi delta x. Okay, that gives us the height at the left-hand end of each one. The right hand is f of xi plus 1, that's the one we've just done. Whereas the midpoint is, as you might imagine, halfway between those two. So, one more concept we're going to look at before we can finally solve this question, which is that the more rectangles we have, the better estimate we have. And that's sort of been implied so far. But let's look. When we have just these four rectangles, and again, this is the right-hand rule, you can see the bits we're missing and the bits we have too much are really quite big. Whereas, if we have, this was 16 rectangles, the little pieces that we're missing and the little pieces that are too much are getting smaller. And the idea here is that as we add more and more rectangles, we get a better and better estimate until we get infinitely many rectangles, and then it will be perfect. Okay, and this is exactly what this is saying here. Okay, if we let SLN be the left-hand sums, SRN be the right-hand sums, and SMN be the midpoint sums, assuming we have n rectangles, then actually as we squeeze these rectangles to get smaller and smaller, get more and more rectangles, it actually doesn't matter if we're going from the left or the right because they all kind of squeeze together. And then we get this very important term, we'll say this one here, which says that as we go to infinitely many rectangles, the summation, this Riemann sum, is equal to the integral from a to b of f of x dx. Because remember, that integral, and this is important, that integral was the area under the curve. So what this really saying is, as we take infinitely many rectangles, it gives us the perfect solution to the area under the curve. What number 3 says here is basically the same thing written a different way. Instead of saying we take infinitely many rectangles, we're saying we take the width of each rectangle going to 0. But of course that has the same effect of giving us the area under the curve, which is this definite integral from a to b of f of x. Okay, so there's a lot going on there. We'll maybe try an example. We'll stick with the same function we've been looking at to see. Okay, so we said, and we've seen some of this before, that if we integrate from 0 to 4, it's approximately given by this summation. Okay, and now instead of taking a set number of rectangles, let's take n rectangles. If we take n rectangles, well, delta x is simply going to be 4 over n, 4 minus 0 over n, which is 4 over n. And the xi plus 1th term is just going to be 4i over n. And therefore, this is our sum. Okay? So I say this is very similar to what we saw before, where we had a fixed delta x for a fixed n. Now we're just taking a sort of a general n. And having done that, the steps we have are pretty much the same. Okay, so first we use the function to find what f of 4i over n is. Okay, we distribute the delta x's and we break it up into two different sums. Again, we can factor the 16 and the delta x and the n's outside, and we get these two terms which we can use our properties of summations on. Okay, so just remind what they are there. And so we can take the sums, instead of sums we can just write them in terms of n's, and then we get a bit of simplification to get to here. Okay, and we can simplify one more time and we get to here. And don't worry too much about the simplifications, I've done those for you. Okay, so we get that the area under the curve, the integral from 0 to 4, is given by 32 over 3, 1 minus 1 over n squared. Okay, we can put in any value of n and find what that is. Okay, but from what we've been seeing, the whole point is that we take the limit as n goes to infinity of that to get the perfect answer. So in this case, we can take the limit as n goes to infinity of 32 over 3, 1 minus 1 over n squared. And of course, as n goes to infinity, this piece goes to 0. So it's just 32 over 3. Okay, and think back to some of the answers we've seen previously. When we're trying to estimate the area under that curve, we saw that it was 10, I think we got 10.625. Well, this tells us the exact 10, so this is 10.66667, 10.6 recurring. Okay, and just a quick reminder what that looked like, to see if that seems reasonable. And it does seem reasonable that the area under that curve would be about 10 and 2/3. So okay, so as I say, we've seen a lot there. There's a lot going on. I suggest maybe go back through the book and read again, maybe watch the video one more time, because this is probably one of the most complicated sections.